Okay, for those of you who wanted to be able to look back over this at home and finish this up, I'm putting this on the internet. So this is our foldable on Newton's laws of motion. Should be on page 15 in your journal. And we have gone over a lot of these. So the definitions here under mass, what I have, and you can have anything else that's similar, but mass is quantity of matter, and you need to have some sort of diagram that indicates kilograms or grams, but the SI unit for mass is kilograms. And then under weight, we talked about weight is the magnitude of an object's weight is equal to its mass times the acceleration of gravity. And the formula is weight is, in this terms, is a force. So F sub W is equal to mass times gravity, or you might also see it mass times acceleration sub G, which is the acceleration constant of gravity. So mag may be another form of how you might see it. Okay? And then you need to have some sort of diagram. Here is my attempt at drawing some sort of weight and giving it something with newtons, because newtons is the SI unit for weight, the force of weight. Balanced or unbalanced is considered an unequal amount of force is applied on one side that overcomes the amount of force on the other. And so again, you need to have some sort of little diagram with a box. The force that's being applied to the box is unequal to the amount of force of friction, and it's overcoming that force of friction. Whereas balanced force, the equal amount of force or pressure being applied on all sides. Now, this is some sort of wall here, and these are arrows pointing on the left side of the wall and arrows being pointed to the right side of the wall, and they're supposed to indicate equal force or pressure on both sides. And whenever we have a balanced force, the net force is equal to 0. Okay? Force is any action that is capable of changing the motion of an object, usually considered a push or a pull. And so we have a wheel of some sort being pushed, and also, there's the force of friction. We'll talk about many types of forces. Net force is the sum of all forces acting on an object. We are going to talk about this. Here's a typical box. You would have air pressure is a force that's all around the box. Maybe the force of gravity that's pulling down on the box. The force of the surface, which we call a normal force. But a net force can be also subtracted or added. So if we have 10 newtons of force going up minus 5 newtons going down, your net force would be 5 newtons. We're going to do some problems to illustrate that topic. Now, gravitational force. I think I crossed some things out here, so I was looking at something else. So make sure you don't write this down. The force with which massive objects attract each other. That should be what you have under gravitational force. Gravitational force on Earth is 9.8 meters per second squared. And again, we use it in the force of weight. F sub W is equal to mass times the acceleration of gravity, A sub G, which it ends up looking like AG, ag, acceleration of gravity. Normal force is force exerted by a stable object in contact with another object. And so I drew a picture here of a person sitting in a chair, and the normal force is the balanced force of a person sitting in a chair. It could be a book on a table. It could be, anything that's laying on a surface of an object. That's considered the normal force. Okay? I do not have tension force and frictional force, so I'll have to come back to those. Magnitude, the amount of something described in numbers, okay? The 5 kilograms, 5 is its magnitude. 10 meters, 10 being the magnitude. 15 meters per second squared, 15 is the magnitude. Okay? Now, free body diagram. This is what we're going to talk about on Monday. Diagram representation of forces on objects using dots and arrows. Okay, so if going back to the book, if a book were laying on a table, okay, the dot is just supposed to represent the book. And so we draw an arrow, line with arrow, and label it as normal force, F sub n, and then the pull of gravity is in toward the ground, F sub g. Okay, we're going to have many, many examples of free body diagrams. Inertia, the tendency of any object to resist changes in its motion. And we've given several examples of this in terms of like metaphors, like your tendency to resist getting up to do homework or getting up to do chores at home, or that's your inertia in other words. But every object on a surface is going to stay on that surface and stay in that spot until an unbalanced force is going to act on it. And so we simply call that its inertia, its tendency to stay there unless you make it move. Okay? So that's also Newton's first law. An object at rest or in motion will remain at rest or in motion unless an unbalanced force acts on it. Okay? So here I drew a circular object on some sort of surface like a table, force, and it's at rest at this point, but then a force comes along and pushes it, it falls off the table, so it's in motion and it hits the ground. Okay? You can draw your own diagram how you want to explain Newton's first law. Newton's second law, the acceleration of an object depends upon the magnitude of its mass and the amount of force applied to it. So we often refer to it as force is equal to mass times acceleration, or acceleration is the force divided by its mass. And we even wrote this in a triangular form in the back of our lab journals, where force is in the top half, mass times acceleration. So you can solve for any one of the variables using this triangular diagram. So Newton's second law is often thought of in terms of acceleration. Any change in velocity, such as speeding up, slowing down, or changing direction. And we did formula or equations for acceleration in the last unit chapter. Acceleration, which is a vector, that's why we have a line across, is equal to the change in velocity, also a vector, divided by the change in time. Okay, or otherwise known as the final velocity minus the initial velocity over change in time. Now I drew some diagrams. This is sort of a summary of the first 6 weeks stuff that we went over. This is our position graph. Notice X, and it is a vector, so this would be position, not distance, because it's in a certain direction. So when we have a position time graph, and to explain acceleration, it's a curve, because it's going one speed, but it's gradually speeding up. In a velocity time graph, it's a diagonal line, because it's increasing velocity over time. Okay? And then this is the acceleration time graph, where the acceleration is constant, so it's a flat line. Okay, so you might want to stop that, pause that, look over that for a little bit. Okay, and then this is a free body diagram showing the same thing, where we have a dot and a longer line indicates a longer distance, and each one of these snapshots is within 1 second. So for the first second, it travels 4 centimeters. Second, it travels 3. The third second, it travels 2 centimeters, and then in the fourth second, it travels 1 centimeter. Mathematically, we could write that as 4 centimeters per second. By 2 seconds, it's traveled a total of 7 centimeters in 2 seconds. And then after 3 seconds, it's traveled a total of 9 centimeters in 3 seconds. And then in 4 seconds, it's traveled a total of 10 centimeters in 4 seconds. So in case you're having trouble seeing this as a speeding up, that it's going a shorter distance within each second, you can do your math here and write it in terms of velocities. So the first, well, this is 4 centimeters per second. Then 7 divided by 2 is 3.5 centimeters a second. So you see how that's getting faster. 9 centimeters in 3 seconds translates into 3 centimeters per second. It's faster than last. And then 10 centimeters in 4 seconds translates into 2.5 centimeters per second. So it started out going 4 centimeters per second, and by the end it was traveling at 2.5 centimeters per second. So this is a free body diagram of how you would show acceleration. Okay? Now, Newton's third law, forces always occur in pairs. That's what interaction means, action and reaction. For every action, there is an equal and opposite reaction. And so you can draw a number of little diagrams here. Anything that a force is being applied, and my artistic abilities are lacking, but you might be a little bit more inclined to about a drawing, but this is supposed to be like a bullet, okay? And the force that caused this bullet to go in this direction, there was also a reaction force after, or once the explosion occurred. So there's always a forward movement, but the reaction force is equal. These are equal and opposite reaction forces. Okay. I think we had 2 other forces that we needed to go back over. Let me look them up real quick. A tension force, especially in a free body diagram, refers to anything that is on the end of a string or a rope. Okay, so you'll see problems about a bucket being hung by a string. Okay, and so the tension force is in the string. Okay? There was also another paper I had around here somewhere. No, that's not it either. So we'll have to find an actual word definition, but we refer to this as F sub T when we talk about tension force, and friction force is the force applied when 2 objects slide past one another. Okay? You can do this at any time by just rubbing your hands together. You start to feel a warming up between your hands. Anything that's rubbing across one another, that's going to cause a friction force. And we label that as capital F sub little f. That's your friction force. Okay? Feel free to go back over any of these as many times as you need to. Stop it, pause it, so it'll give you time to write it down. But I'm going to let you use this as your time to put this into your foldable.